The strangest force in physics is the one you feel every second. Gravity holds your feet to the ground, pulls rain from the clouds, keeps the moon circling Earth. Gravity keeps the moon circling Earth, and it keeps Earth circling the sun. You do not need a laboratory to notice it. Just drop a pencil. Jump in place, or watch ocean tides, and gravity is already there. And yet, when scientists open the most successful map of tiny reality, gravity is not inside it. That map is called the Standard Model. It describes the particles that build matter and the invisible interactions that let those particles communicate. It explains why atoms hold together, why light interacts with electric charge, and why some particles decay into others. But the force that shapes planets, stars, and galaxies is missing from the table. At first, this sounds impossible. If gravity controls the largest structures in the universe, how can our best theory of particles leave it out? In everyday life, gravity is a constant, pulling force. But in the tiny world of particles, everything changes. Here, creating a mysterious subatomic dance. It feels powerful because it dominates large objects. It makes mountains heavy, gives planets round shapes, and gathers gas into burning stars. On the scale of atoms, gravity becomes unbelievably weak. Think about a small magnet lifting a paperclip from a table.
This tells us something strange. Gravity rules the cosmos because it always attracts, and because huge amounts of matter add their gravity together.
But between individual particles, it is far weaker than electromagnetism, the strong nuclear force, and the weak nuclear force. These four forces are the basic ways nature changes motion and structure. Electromagnetism holds electrons near nuclei and allows chemistry. The strong nuclear force locks quarks inside protons and neutrons, then helps bind atomic nuclei. The weak nuclear force allows certain particles to transform, making processes like radioactive decay and the sun's energy possible. Gravity holds you down, guides planets, bends light near massive objects, and builds the arc. So the mystery is not that gravity is unimportant. The mystery is that it is too important to ignore, yet too different to fit easily. The Standard Model can describe three forces using quantum rules and messenger particles. Photons carry electromagnetic interaction. Gluons carry the strong W and Z bosons carry the weak interaction. But when we ask for gravity's messenger, the table becomes silent. That silence is what makes this question so deep. The force you feel most directly is not the force particle physics understands most easily. Gravity is familiar on the surface, but mysterious at the bottom. It behaves beautifully in Einstein's description of space and time, yet resists the particle language that works so well for the other forces. Before we can see why this happens, we need to step inside that particle language itself. We need to open the Standard Model and ask what it actually explains, which particles it contains, and why three forces fit there while gravity remains outside. Only then does the missing piece start to look truly surprising. To understand why gravity is missing, we first need to see what the Standard Model is actually doing. It is not a theory of everything. It is more like a beautifully organized map of the microscopic world, showing the known elementary particles and the quantum rules that govern three of nature's forces. On this map, matter begins with two families, quarks and leptons. Quarks are the particles that combine to make protons and neutrons, the heavy pieces inside atomic nuclei. Electrons, which move around nuclei and help form atoms, belong to the lepton family. There are also neutrinos, ghost-like leptons that pass through matter almost unnoticed. Together, quarks and leptons are the basic matter particles in the Standard Model. But matter particles alone cannot explain reality. Particles must interact. They must attract, repel, bind, transform, and exchange energy. In the Standard Model, these interactions are described through quantum fields and special messenger particles called photons. For electromagnetism, The messenger is the photon. When charged particles interact, the photon is connected with that interaction. This is the force behind light, electricity, magnetism, chemical bonds, and the reason your hand does not pass through a table. In daily life, we notice objects as solid. At the microscopic level, that solidity is mostly electromagnetic interaction between atoms. For the strong nuclear force, the messengers are gluons. Gluons bind quarks together. Inside protons and neutrons. Without them, the nucleus of an atom could not exist. This force is incredibly strong, but it works only across extremely tiny distances. That is why it dominates inside atomic nuclei, but does not pull your coffee cup across the room. For the weak nuclear force, the messengers are the W and Z bosons. This force allows certain particles to change identity. It plays a major role in radioactive decay and in the chain of processes that allows stars like the sun to shine. It is called weak not because it is unimportant, but because its range is. So the Standard Model explains matter and 3 quantum forces with amazing success. It describes what happens inside atoms, inside nuclei, and inside particle accelerators. It has predicted particles before experiments found them. It helped scientists understand the Higgs boson, a particle connected to the Higgs field, which gives mass to many elementary particles. It can even tell us, with remarkable precision, how particles scatter after collisions, how unstable particles decay, and which interactions are allowed or forbidden.
This is not just philosophy. It is tested in machines, where particles are accelerated close to the speed of light and smashed together,
leaving tiny tracks that reveal the rules underneath ordinary matter. That is why physicists trust the model so deeply.
Our understanding of the universe is vast. We have mapped out particles and forces. Even while knowing, it is still fundamentally incomplete.
This is why the missing gravity problem is so strange. The Standard Model is not a weak or careless theory. It is one of the most accurate scientific frameworks ever built. Yet it remains almost completely silent about the force that pulls planets into orbit and bends starlight around galaxies. The contrast is sharp. In the microscopic world, the Standard Model gives us particles, fields, interactions, and precise predictions. In the cosmic world, gravity is simple, but our universe has 2 different rules, and they speak completely different languages. To understand reality, we need to bridge this gap. The Standard Model asks, which particle carries the force? Gravity, as we understand it through Einstein, answers in a completely different way. It does not simply behave like another invisible message passed between particles. It seems tied to the shape of space and time themselves. So if 3 forces can fit into the particle map, why does the 4th refuse? To answer that, we must look at what makes gravity different. At first, it feels natural to treat gravity like the other forces. Electromagnetism has photons. The strong force has gluons. The weak force. So why not imagine gravity as just another interaction, carried by another tiny particle? This simple idea is tempting, but gravity has a different identity.
Pulls. The Earth pulls you. The sun pulls Earth. A black hole pulls light. Nothing can escape.
Mass and energy bend space and time. Gravity is just the shape of space. It directs how objects move.
Imagine 2 people walking across a perfectly flat floor. If they move toward each other, you might think some invisible force is pulling them together. But if the floor itself curves beneath them, their paths can meet, even if nobody is pulling. In Einstein's picture, planets do not orbit because the sun grabs them with a hidden rope. Instead, mass bends the fabric of space, and gravity is simply geometry. They follow curved paths through spacetime, shaped by the sun's mass. This is where gravity becomes strange for the standard model. The other forces happen within spacetime. Particles exist in spacetime, moving inside a fixed spacetime box. Fields spread through spacetime, and force carriers travel through spacetime. The stage is already there. But gravity is connected to the stage itself. When gravity changes, the geometry of the stage changes too.